Okay, so welcome everybody to the afternoon session. We are about to resume our interesting series of talks today. My name is Max Zanin, and I will be the MC for the next session today of the afternoon. For those of you who still don't know me, I'm a kind of a hybrid academic because I developed my career as an academic at the University of South Australia, and I now hold the position of adjunct associate professor at both Uni of Adelaide and University of South Australia. So I should say I'm very well positioned for next year for the merger because I have 1 foot here and 1 foot there. That's ideal position. Besides my academic activities, I also do some consulting through MZ Minerals, which is my consulting company, to the mining industry, specifically around flotation. I'm a flotation expert, and I look into grinding and flotation circuits pretty much everywhere, and I crossed my paths with Chris many times. Interesting conversation with him. Anyway, we are going to resume, and I have to invite again, Professor Simon Ratcliffe on stage. I don't need to introduce him again because he was already introduced by Nigel. He will going to give a talk titled 3 PRIF Project Case Studies and Industry Perspective. So welcome, and I leave the stage to you.
All 3 unique projects. So allow me to reminisce over the next 15 minutes while I recall and reflect on the 3 main projects that Maptek was involved with over the lifespan of the PRIF. 7 years and counting, no less, with a COVID pandemic arriving right in the middle of it, as we all know. But it doesn't really seem like 7 years. Time flies when you're having fun, I think. So the projects that I'm wanting to talk about are just my personal recollections, 3 of some 25 projects. So it's really just a small view of the PRIF through a drinking straw, if you will, just my personal views on it. But I think some of the reflections and themes that I touch on are going to resonate with people in the room and their experiences with their projects as well. So not so much a presentation from me, it's more, I'm calling it a post-luncheon fireside chat. This is a wood engraving from 1855, and it depicts a scene in New England, I think on the border of Massachusetts and Connecticut now. And I stared at this quite a bit when I was preparing for this presentation, and it struck me that the scene is rather reflective of the PRIF. There are several groups of people here doing different activities, but all the activities are related and taken collectively. They're working on the well-being of their household and possibly more importantly, the well-being of their wider community. And that's not a bad way of looking at the PRIF, is it? I stared a bit more and I thought, well, okay, so which character am I in the picture? And you might want to play the same game for yourself. I've ruled out myself being the parrot hanging from the ceiling. Also the dead animal, somewhat unfortunately pinned to the far wall. But there's plenty others there to choose from. So look, coming into the PRIF, I think it's fair to say that Maptek was a well-intentioned but somewhat reluctant translation partner. We'd never been involved in anything like this before, and we found the scope and scale of the PRIF a little bit unapproachable, and the integration ambitions that were there and the uncertainty around some of the outcomes were, well beyond something that we would attempt to do commercially. And this this was a great learning thing for us because it will introduce me and my colleagues to a research community and a way of thinking about the kind of things that Peter was talking about in his presentation. And this was across academic disciplines in mining engineering, materials processing, metallurgy, chemistry, mathematics, and of course computer science. And it led to a fairly fertile environment for learning and discussing. And I think that was one of my earliest recollections. But in terms of something tangible, the first thing that Maptek got engaged with was, something that was quite easy to sell to my bosses, and that was a sales opportunity. So we move on to project number 1. This was a project that, this was part of Larissa Stetsenko's project, and I actually got in touch with her leading up to this presentation. I think she's still in Europe at the time and wasn't able to make it back in time. But she was looking at trying to quantify the in situ resource heterogeneity. So let's know better the geology that we're mining so that we can better understand what we're going to be feeding to the downstream processes in the mill and reduce the uncertainty around that mill feed. And her idea was to take a Maptek SR3 laser scanner that's used for underground geotechnical analysis and replace the imaging component, the camera inside the scanner that just captures a little RGB value for every pixel, and replace it with a hyperspectral capability. So could we fit a hyperspectral camera to a Maptek laser scanner? And we quoted a laser scanner, thinking we'd be able to sell one to the consortium and it would have a lot of use through the life of the consortium. Larissa did a bit of work on hiring, and the costing, hiring a hyperspectral camera. We started some engineering work around integrating the hyperspectral camera onto the laser scanner. Getting to site proved extremely difficult, and this continued to be the case through the PRIF. The guy pictured in shot, Maptek colleague Lance Steele, he'd been doing some work at the Fosterville mine just out of Bendigo, a lot of underground geotechnical work, and he figured we could get on site there. So we did some preliminary engineering, and soon physics just hit us in the head. We realised that the illumination required for a hyperspectral camera was vastly different than the illumination you need for a visible camera. The wavelengths of hyperspectral go from the far infrared up to the UV, and you need even high intensity illumination across that spectrum. And there was no battery technology that was going to be able to power the lighting required. I think we at the exposure times we were looking at, it was some 80 kilograms of lighting equipment, and it needed a generator to run it. So very, very quickly on, physics bit us, and therein ended Maptek's involvement in this particular project, and the project went on and diversified and did other things. I certainly don't regard it as a failure. I mean, I regard it as a success. The early research and engineering work uncovered the physical constraints to prove that it wasn't a goer. And this started in late 2017, in the very early days, and sort of left the agenda in early 2018. So the early part of 2018 was fairly quiet for Maptek from the PRIF perspective, and things were getting signed, and there was, a bit of to and fro around IP. And to the university's credit, they were helpful at listening to our suggestions and kind of said, well, yeah, the commercialisation part of it is fairly new to us as well, so we're happy to listen to you, and that was a really good thing and really helpful. I think it was after the first research conference, mid or August maybe 2019, a couple of days afterwards, I got an email from Frank. And Frank, I'm going to paraphrase you here, Frank, but you sort of had in the email, well, Simon, you're a mining guy. Have you got any interesting optimisations problems in mining that we could work on as part of this PRIF? And I did have one in mind, and I invited Frank into Maptek, and Frank brought a couple of his then PhD students. I think Hirad was one of them, and I think Yui was there as well. And I started talking about two technologies that Maptek recently had invented and acquired. One invented, one acquired. The first one was a machine learning algorithm that was able to predict geology. And so it was based on AI, and like most things in AI, it's probabilistic in nature. And that means every time you run it, it gives you a different answer. Now, that's not necessarily an attractive thing, but it can actually be quite an advantage, because if you run it multiple times, you get this ensemble of results, and by studying the statistics of the results, you can get a handle on geological uncertainty. We also had a mine scheduling package called Maptek Evolution, and that enabled you to optimise the net present value of an open cut mine through the order in which you mine out the pits. And it was designed to run on a single model of the geology. So the natural thing to do was to run it on multiple models of the geology and somehow modify the optimisation to minimise the downside risk. You know, if you happen to get unlucky, can we use the optimisation in such a way to minimise the uncertainty around the geology? And we didn't know how to do it. Now, Frank and this project really gained some momentum in 2019 when Aneta joined. Aneta had been publishing some theoretical results in this area, and it could inform what we could do to the algorithm to take uncertainty into account. And I think a PRIF translation project was born out of this. It was a little bit off the initial radar of the PRIF because it was open cut mining, and none of the partners were into open cut mining at that stage. And one of the great things that happened is during the course of us working on this, BHP started working on the economics of their West Musgrave nickel deposit, and the Maptek Evolution software ended up being used for economic studies there. So it sort of came back around and turned out somewhat fortuitously really well. So this was one of the early outputs from some development work that was done by the Maptek Evolution team, funded at cost from monies from the PRIF. And I have to say that cash, that money coming from the PRIF into a Maptek development team was absolutely critical for me getting this on the agenda at Maptek, getting up that roadmap and onto that roadmap list that I was talking about before in the panel. And that let us get some momentum into this project. Will Reid, Luke Berry, and Mike Stimpson in the development team got busy on this, and this was one of the first graphs that I saw. And as soon as I saw this graph, I really knew we were onto something, because this is the sort of information that enables miners to make better decisions. You can see there are some years where geological uncertainty is not having a big effect. There's quite a tight cluster here. But there are other years where there's this huge spread because we're mining out areas that are not yet well enough studied to understand the economics. And just presenting all of these runs on the same graph was really informative. This is before we did anything with the optimisation algorithm. Now, I think it was in October that year, 2020 perhaps, where the funding ran out. And I think, Nigel, you approved the last tranche of payment that went a bit above what we initially allocated. So thanks, Nigel, that was very helpful. At that point in time, the project had gained a foothold, a momentum within Maptek. Frank and Aneta's research was starting to come to the fore in terms of how we would then take it. So the funding really didn't matter after that. It got a life of its own and kept on being developed. And I think, Frank, you took the opportunity to pounce on us then and suggested to Will and myself, well, why don't we write a paper? And you introduced us to the dark arts of paper writing and taught us about overleaf, LaTeX and all of that. That was all new to us. I think Annette have very patiently took Will and I through how to use the system. And we ended up publishing 2 papers. Will was the primary author, Annetta, Frank, myself, and I think Annetta presented at 2021 Gecko, one of the papers, and the second paper was at the IEEE CEC conference in 2023. And that was a lot of fun. That was great. Now, the capability in the software is it's not out there making money yet because the industry is still not ready to take a probabilistic geological model all the way through the mine planning and economic optimisation process. But it is very latent. I believe it will have its day in the sun in the not too distant future because the value of these probability models is being shown time and time again to be extremely high. All right, the third project I want to touch on happened again after one of the research conferences, and this time it was my turn to write an email. And I saw this fella get up, there he is over there, Yerniyaz, and he presented on his hybrid domain modelling framework under Professor Peter Dowd and Professor Chao Shui Zhu, and it had a lot of overlap in some ways with the AI model that we'd come up with for predicting geological domains. But I saw a great complementarity to them. So I wrote Yerniyaz an email and said, well, do you want to come into Maptek? And we got talking. I think, Peter, you came to that first meeting as well, along with Chao Shui. And the idea was born that we would be able to at least offer you tools for visualising the work. And you were well into your PhD by then, but at the conclusion of Yerniyaz's PhD, the idea of taking Yerniyaz's PhD and putting it onto a computing platform that would enable it to be easily commercialised and elastically scale to many users who want to use it around the world, that idea was born. And I don't know if anyone here remembers my presentation at the last research conference. I had that big burly guy with the drill trying to commercialise his algorithm and not getting anywhere, and suggesting that Maptek had a platform that enabled people like Yerniyaz to easily commercialise their work. That idea was born. And I don't know the outcome because Yerniyaz has gone dark on me in the last couple of weeks. It's been a race against time, and he's probably been not telling me the outcome because he's actually the next speaker. And, you know, I'm not going to... I can't steal your thunder, Yerniyaz, because I don't know the answer. So learn more about how that's turned out in the next presentation. So yeah, that's 3 projects from Maptek. What I might do is just backtrack to this image so you can think about who you are while I sum up. The 3 projects are interesting, aren't they? Because the genesis of all 3 is quite different. All 3 have exhibited changes and pivots along the way. And I think the ability for the PRIF projects to do that has been absolutely fundamental. And I think it's been built on the trust relationships that we've managed to build up amongst all the collaborators. So that would be my key reflection, is that the ability to be adaptable and to pivot is predicated on trust, and it's very clear that the PRIF had that trust, you know, right the way along. So I'm going to leave it at that, but I'm very happy to take any questions. Yeah, I did, Frank. Sorry, Nigel, I did. I'm the young lady on the right there, staring into the fire, intently staring into the fire, waiting for the next big idea. That's me. How about you?
I don't know, I suppose.
It's a fascinating picture, isn't it?
Think about it. I guess the guy sitting there on the table.
The pensive guy staring into the
Pensive guy there
candle?
with his hand like that.
Yeah.
I guess identify with him more than anybody else.
Interested to hear everyone's comments on this one.
We should pass the microphone around now.
Thank you for the very aspiring presentation you have got here. I got a question about your project one. I'm curious about, I also use hyperspectral imaging laser for agricultural purpose, more about that. I'm just wondering, like, for your hyperspectral imaging, you got more channels than you need, I believe. So do you know what do you want to look at in there? So you may be able to customize the channels rather than using the full spectrum, hyperspectral imaging. And then you can reduce the light information requirements.
That's a nice idea, yeah. I guess you could imagine a system where you would go underground with a full spectral light source and do a full hyperspectral study, use that to train some mineralogy classification, and then decide on the frequencies that are most important, and then only illuminate using those frequencies. I think that's quite a nice idea. I also think that the time for doing this underground is yet to come, because these hyperspectral sensors are getting more and more sensitive, and light sources are getting more and more efficient. So at some future point, there is going to be a sort of a crossing over there to make this viable. But as far as I know at the moment, all of the hyperspectral applications that I know of use the cheap light source that's here during the day, which is sunlight. I don't know of an underground system that's using hyperspectral. If anyone does, I'd be really interested to hear about it. Yeah.
Okay. Any more questions? No question, then. Oh, you want to do it? Okay.
Yeah, thank you.
All right. So speaking of the David, the next speaker is Yerniyaz. So you were spoiled already because you'll be introduced, but actually Dr. Yerniyaz is one of the PhD students within the PRIF, and he's going to present his work. He's now postdoctoral research fellow at the University of Adelaide, and he's going to present his work in hybrid domaining frameworks. Yerniyaz, as I said, is a recent PhD graduate, and he's passionate about geostatistic and geological modeling. He's currently pursuing advanced research in geological domain modeling and data science in geostatistics. He's committed to lifelong learning and pushing the boundaries of knowledge in these dynamic fields. From the PRIF specifically, Yerniyaz has personally gained knowledge and experience, hard and soft skills, and also life friends and all-round mentors mostly. His greatest achievement during PRIF is his successful PhD, resulting in potential commercialization with Maptek, as we know now, who's a leading provider of innovative software, hardware, and services to the mining industry. So welcome, and the stage is yours.
Yes, thank you, Max, for the introduction. And thank you to Simon to not give spoilers to the audience. Anyway, so my name is Yerniyaz Abildin. Today I'm going to talk about hybrid domaining framework. Okay. So this is the result of my PhD, which was the constraints and quantifying uncertainty on resource domain boundaries in general. And the project objective was to reduce or quantify the uncertainty on domain boundaries in order to reduce overall uncertainty in resource model, and which will further impact the mill feed and other specification required. And it's under the exploration evaluation section of whole mine value chain. So just imagine, what if you have one geological map, then with machine learning, less used machine learning, and add more machine learning, and in same data you get something different. So today I'm going to talk about first half of the presentation about this, which is PhD stuff, and later about my collaboration with Maptek. And just brief background information. Mineral resource estimation consists of 4 main stages, and the second one, which is geological modeling or domain of interest, which is prior to the estimation or simulation, is directly related to my project. And overall framework look like this. Basically, we have grades and lithology or rock types, any categorical variable used, and we have geostatistical simulation in order to get the estimation for the grades, do some pre-processing, and at the end combine into the classification and obtain probabilistic domains. This is the very straightforward and easygoing graph. And when we did our case study on South Australian IOCG deposit, we had 20 elements as variables, as numerical, basically variables, features. Then get our simulation results. Afterwards, in the same time, we trained our classifier on those 20 variables and 12 classes. And our classifier showed like around 80% accuracy, which is really good in general with real data, and obtained, for example, this 3D image on the right is the most probable outcome of the hybrid domain framework. And on the left side is a reference model. It's not like apple-to-apple comparison. It's probably more orange to apple. So that's why you can see that the features are aligned, but not all of them. So now you can see that, for example, in the reference model, we can see the dolerite is very smooth and continuous, but in most probable is not, because dolerite is itself, I mean, the methodology itself is data-driven, and we have less samples which represent the dolerite. That's why we have some problems with continuous features, but overall big features you can see is represented well. And the good thing is that we can provide the probability maps, and along the dolerite zone, you can see that there is a low probability compared to the dolomite, which is dark blue, and hematite, which is yellowish color. Yeah. And what was the key or novelty is the pre-processing, as shown in previous graphs. And the real problem in my site was that there was a high misclassification rate between 2 lithologies. And by mitigating this, basically reducing some of the, or removing some of the samples and relabeling some of the into the corresponding correct lithology, we gained twice more samples in one class and a little bit less in other class. And voila, our map changed. So it means that with more machine learning, we fixed our misclassification rate. And in MineSight, we went to the core logs and checked, is it right? And it seems valid. And this data-driven approach can mitigate some of the human error in general. So this is the novelty of the method itself. And also another thing that we can provide uncertainty, which is also really good. So before pre-processing and after pre-processing is clear now. And this is in essence, hybrid domain framework. And what's happening now is I'm working with Maptek, getting things, the parts or the components of the HDF into their commercial geological modeling product, which is domain MCF. And now all codes are operational and within Maptek environment. Just we are working on the refactoring optimization, because I'm no way a software engineer and can provide production level code, not near. So yeah, and hopefully which will lead to the commercialization. And this is the team that I'm working with and happy to work further. Yeah. And I would like to acknowledge my supervisors and user partners and translation partners and other partners as well, So you think this is the end, but it's not, because we have a bit of demo. So, but before demo, I would like to say that in Maptek, there is a strategic initiative which is intended to help Maptek develop data-centric solutions. It's essentially an ecosystem of 3 platforms, which are MDS, Maptek Data System, MCF, Maptek Compute Framework, and MAE, which is Maptek Automation Environment. I'm directly working with MCF and MAE in general. And when it comes to the HDF, which will be integrated into domain MCF, geological modeling product based on the neural network algorithms, HDF will be kind of alternative, or can be consensus-based implementation within the domain MCF. And domain MCF sits within the MCF, which is Maptek Compute Framework, and it gets data from MDS and so on, so on. This is a bit of the process going on, but overall, what allows me to implement is that, for example, in MCF, I have these 5 operations, which is variable forward transformation, sequential Gaussian simulation, then back transformation of the simulated variables. Meanwhile, also I can train my classifier, and later on combine everything and predict in the classifier. So there is some, if you want to look under the car hood, I can show during the demo session. I brought my 2 laptops for Linux and for Windows. It will be interesting. You approach it to me, please. And for example, this is how it looks like in MAE. We set up our output pass, input, and what we get at the end. And there is some intermediate parameters that we need to pass anyway. And in simulation, for example, we need to pass the block sizes, nodes, and other stuff, variograms, for example. And now what we're working on is trying to connect everything and make it one streamlined process, because every operation is separate, everything has own unit tests, and now we're testing edge cases, sometimes fixing bugs, probably most of the time. But anyway, this is how it looked like, and it's really convenient for me, who is basically mining engineer working in geological modeling and going to integrate my PhD into the basically global software provider in the mining industry, which is very convenient in general, and thanks to that. And the key advantage again, why is this image here? Because it's a parallelization. What I had in my PhD is the problem of simulating 20 variables in a sequential order, which means that I have to spend one variable, wait when it's done, then start next one, and like it's 20 times. And there wasn't any batch processing. So sometimes I set my alarm at 3 a.m., okay, put my next variable, because we are like close to the deadline, and so on. But now what we can do, since those operations are separate in the MCF, we can just set 20 instances and run parallel, and also train the stuff as well. At the end, we just need to combine in the predict operation, and that's all, which is hopefully make geologists' life easier and some PhDs as well. So, yeah, thank you. Thank you for that. Any questions?
So, Yerni, am I right in understanding that each pixel is classified by the data behind each pixel regardless of its neighbors?
Yes, classified. No, the classification doesn't include any coordinates, so there is no special element, but the simulation includes. That's why there is indirectly we incorporate special continuity into the process overall.
Right.
Yeah.
Because I was going to ask, because I've seen a lot of image analysis and computer vision stuff in the last couple of years where they're trying to interpolate structures that are hidden behind features on imagery. And I was wondering whether you felt that was reliable enough and robust enough to implement into a resource domain modeling system yet.
Yeah, actually there is a way. The problem is most of them still use some of the Kriging residuals. So it means that anyway they're imposed by the variogram. So simulation in that sense is more advanced. and you can cover the extreme values, which are probably important in some of the classes, but not the major ones. Yeah.
Any more questions?
So what is the future for the HDF in AI space?
Now plan to implement everything in the MCF, I mean domain MCF. Then later on, add those pre-processing that I had in my PhD. Also, since there is a room to get a lot of stuff in MCF in an easy way, we will do a lot of experiments, getting more algorithms, and probably there will be automatic variogram fitting and post-processing and other stuff which are in the ML field are available now. Yeah, thank you.
Okay, so thank you very much. Okay, so now we move to one other very interesting project from the PRIF, which is aiming at generating impact to the industry and commercialization. And it is the project of Dr. Difan Tang, who will tell us how you can turn a rod into a probe to sense, in particular, particle size. So Dr. Difan Tang joined the PRIF mining consortium as a postdoctoral researcher, undertaking the hydrocyclone particle size measurement project, which is where he devoted all his energies over the last few years. And his research interests are in advanced and affordable online particle size sensing. And Difan considers participating into the invention of a new sensor as being a great honor, an opportunity that can make a change to the mining industry. Additionally, his new sensor has successfully attracted the attention of his 5-year-old daughter. So that's also very interesting, Difan. Good to know. She thinks it's magic. It's magic, and she wants to become a scientist too in the future. So very, very nice achievement, Difan. Not only improving the industry, but also your family aspiration. That's very nice. So welcome, Dr. Difan Tang, and I leave the stage to you. Thank you.
Thank you, Max.
Is this a magic wand?
Good afternoon, everyone. My 5-year-old daughter thinks that's a magic wand because I told her this tiny rod could help people make more money. In this presentation, I'm going to show you how we turn this ordinary rod into a useful probe that could help you grow your revenue. If you have seen our presentation in the past years, then this year you may find this probe more powerful than before. So our project deals with hydrocyclones, which sits within the comminution circuit, playing an important role linking comminution to flotation. Then why are we monitoring the particle size at hydrocyclones? That's because optimal recovery rate at flotation requires an optimal range of particle size. By grinding to the right particle size range, we can either improve the throughput at the same energy consumption level or reduce the energy consumption at the same throughput. Also, particle size is one of the indicators that tells the operation status of hydrocyclones, which can be used to detect and prevent hydrocyclone faults that cause the production loss, which can be about 5% to 15%. So if you're answering yes to all the questions here, then our technology will be right for you. So take a look at the BHP Olympic Dam 2023 copper production, for example. Let's be conservative and assume just 1% of throughput increase, and you would be looking at an increase in the revenue about $20 million. If we consider only 1% of prevention of the throughput loss due to hydrocyclone faults, then you will be looking at an additional $5 million. Now, how much does our sensor cost? You'll be looking at that tiny amount. And the benefits is huge. And bear in mind, that benefit is per annum. So you might be wondering why we still need to develop a new sensor when there are already some existing product doing similar things in the market. A very simple reason. The sensing system needs to be cost-effective. Our sensor can do multiple things, it's multifunctional. So having one sensor is equivalent to having multiple individual different sensors at the same time. And it is constructed in a way that can reduce the cost significantly compared to its counterpart in the market. It operates just like your finger with different sensations. We won't put your finger into a slurry, but we use a rod instead. But the rod itself does not have any feeling. To make it live, we attach force torque transducers and accelerometers on the probe to make it capable of feeling things from the material that it touches. Here is how it is intended to be used on the mine site. Normally, the comminution is operated in an open loop. Open loop means the particle size information, there's no feedback of particle size information or significant delay in feeding all the information back to the operator. And as a result, there's a large variability in the product size. So with the sensor putting at the end of hydrocyclone, we can feed those information back to automatic controller, which can then tell the system what parameter it can operate optimally so that we can minimize the variability of the product size. And by doing so, we can produce the right size range for optimal recovery rate at flotation. In our lab, we use a small-scale system to do tests. The system can be easily scaled up to a larger pipe. As you can see at the back of this room, or in front of our poster, there is a prototype installed on a larger pipe. And the installation position can also vary, horizontal, vertical, different angles. We have a video demo in front of our poster as well. So the figure on the left side shows our very first outcome 3 years ago. The sensor was initially designed to give a single number that tells the size passing fraction. For example, if we know we can read from the force measurement and given all the existing known parameters operation, then we were able to tell the passing size. And sometimes it's desired to know the detailed distribution of the particle size. And we have been putting effort in making this possible in the past years. And the outcome is promising, as shown on the right side. Our size approximation is very close to the benchmark done by laser sizing. The error is about 7% to 10%, and that is within the range comparable to our counterpart, acoustic counterpart, available in the market. I have mentioned earlier, this year you will see this sensor more powerful. Here is, we have extended our sensor to dry mineral processing. Nimble Resources is operating alluvial gold mining using their novel rotary air concentrator This is their new invention and needs a lot of work to do for optimization. And they're looking something to tell the controller for the optimization, and that's a density measurement. Why density, not particle size? As can be seen from the top right corner, the concentrates and tails share a significant amount of particle size within the particles with the similar size range. However, by looking at the density, we can see distinct difference between the concentrates and tails. And also looking at the discharge material flow of concentrates is high intensity in free fall by gravity. And that renders most existing technologies like laser optics, photo imaging processing, or ultrasonics ones very difficult. But our sensor can fit in this application well. And the red dot shows where we are going to put our sensor. That will be at the end of the 4 concentrators to monitor in real time the particle density of the concentrates, so that information can close the loop for the controller to optimize its operation. In our laboratory, we use the same sensor on the left side, and also put that underneath the hopper on top to simulate the material flow in free fall. And the hopper is controlled by a computer to motorize a plug that can adjust the opening of the hopper to change the mass flow rate in real time. What do you see in this figure? I can see gold. Look at those bright, shiny, golden peaks along the ridges. Those peaks indicate high-intensity particles with high density. So our job was to quantify material flow, the mass flow rate, particle size, and density from the data, while getting rid of the disturbances from the coupled variable like the mass flow rate change. Now let's look at 2 scenarios of different mass flow rates. Despite the difference in mass flow rate, we have consistent and relatively stable density measurement as shown at the bottom 2 figures. We can also see some transient overshoot. That's the normal phenomenon as a transient response in most dynamic systems, and won't cause any issue for the density measurement because they only happen at the beginning of measurement. Now let's have a look at the measurement of density change. To simulate the density change, first we load the hopper with concentrate, followed by tails on top. Initially, after the transient period, our system records the density of the concentrates. Soon after, the tails start to mix into the flow with the concentrates. We can see drastic decrease of the measured density until all the remaining particles are tails. So this is exactly what we need to be integrated into the rotary air concentrator system for its optimization purpose. Now you have seen our sensor in dry applications and wet applications. It suits a range of applications as long as particle size analysis is needed. And we are looking to install and test our sensors on real machines, such as hydrocyclones, vertical roller mills, and rotary air concentrator to demonstrate its value. In the end, I would like to acknowledge the support from my supervisor, our end user partners, and translation partners. And special thanks goes to Lin Yang from the ARC Training Center for his help in lab work, and also Richmond for his help organizing mineral processing facilities to facilitate our tests. And last but not least, my acknowledgements go to the Consortium for the tremendous support throughout the 4 years of research journey. That's all of my presentation. Thank you very much for your attention.
I like this.
Very interesting. I guess that everyone likes this. So is there any question for Difan? Yes.
Howdy. You focused, I guess at the start, you pointed out the cost of your sensor. At the same time, you were showing how much increased revenue can be created. So if I put it to you that cost is probably not the main concern for a mining company that may be able to make that much more revenue from your sensor, what are some of the other areas that it beats the competition at? For example, and you may have covered some of this in the presentation, but flexibility of installation, reliability, or quality or scope of the data that it can produce. Out of those sort of topics, is there some other key performance advantages?
Yeah. There are some technologies that are potentially applicable, like laser optics and ultrasonics ones, but those machines require additional sampler, and so that makes it bulky and needs bespoke installation, and the cost is high as well.
Yeah, so that's more flexible installation options. And have you had it in the field long enough to look at the reliability difference between your sensor? I mean, it strikes me that laser and ultrasonics may need more frequent calibration. Have you got any data on frequency of calibration or reliability, sensor failing type information?
Yeah, calibration is required. The closest counterpart of our technology is an acoustic variation developed by a company in Canada. Our calibration scheme is similar to theirs. According to their claim, the calibration is one time only. So, but it depends on the quality of the initial calibration.
Okay, thanks.
Any more questions? Well, if there is no more questions, just let
Can we sign your daughter up for a PhD?
That'd be great.
Thanks, Difan. That was a great talk.
Yes, well done. Okay, so next we have Abhishek. Abhishek is a master's student from the University of Adelaide, so he's at an earlier stage of his career compared to Difan and the other ones, but he's very passionate, and he embraced the project about maximizing SAG and AG throughput in mills with online mill integrity analysis. So as I said, he's a master's student at the University of Adelaide, and through the PRIF program, he will gain experience in conducting cutting-edge research in the field of mining engineering. So far, he has developed a deeper understanding and advanced monitoring techniques, finite elements analysis, and learned to apply theoretical knowledge to practical real-world problems. And also working with interdisciplinary teams, which is very relevant and important. So his greatest achievement during the PRIF has been the development and validation of a real-time vibrational analysis system for SAG and AG mills. And today he will present his findings. So this research aligns with the PRIF's mission of fostering innovation and improving industrial processes and marks a significant milestone in his early research career. Welcome, Abhishek.
Thank you for the introduction. So good afternoon, everyone. I'll be presenting the work done in my master's project, that is maximizing SAG and throughput with online mill integrity analysis and monitoring methods to minimize shutdown. So this comes under the combination section of the whole process, and where we focus on the mill operations itself, with the main objective being the fault detection in SAG mills through vibration analysis. So talking about SAG mills, they are utilized to pre-process any large materials. They are in continuous operation 24/7. They are fed a steady load at an optimal RPM. As they are operational all around the clock, any shutdown of these mills can cost the operating company tens of thousands of dollars. These shutdowns are mainly scheduled due to the liner degradation inside the mill and their maintenance. Talking about the liners are degraded through friction due to continuous grounding. As you can see in the picture on the left, this is how a basic liner profile looks like. And picture on the right shows the liner wear over time, how the line height reduces when it grinds over time. And this reduction in height directly influences the output of the efficiency of the mill. So the main challenge that is being faced is obtaining the information of the shown liner degradation status while the mill is on operation. The current method involves scheduling mill shutdowns for liner inspection and replacements. And the current methods involve hands-on approach, measuring liners, and laser scanning as well. As seen in the picture, whenever a person goes to check the liner degradation in the mill, there are certain liners that are under the load which cannot be visible to the person inside. And that is one of the main drawbacks of the current methods that exist. Talking about the current methods, as I said, the first method is the hand measurement, where the profile of the line measurements is done manually. The second is laser scanning, where, as the name suggests, the mill interior is laser scanned with spatial data and compared with the original data and see how the liner has degraded. The proposed method which we worked on is the vibration analysis, where we will use the SAG mill vibrational data, collect the data, and process it to determine the liner health. It is a non-intrusive method that will help reduce the overall downtime of SAG mills. In the first and the second picture, as you can see, the first picture depicts the laser scanning and the second picture the measurement. In this, the person has to be physically present in the mill, so the mill has to be shut down. So it is an intrusive method. As compared to the third picture, where we place the sensors on the surface of the mill, thus it becomes a non-intrusive method, and thus there is no shutdown involved. Based on these observations, as I said earlier, the objective is fault detection in the SAG mills through vibration analysis. The steps involved is firstly the model verification, where we set up a theoretical model and verified simulation. And then we simulate some scenarios to see how the frequency varies when we remove a liner, if we change the height of a liner, and how the frequency fluctuates because of the structural load. So the approach to this is we consider the SAG mill as a thin cylindrical shell and study the various theories that are present in literature for said shells. And we perform the calculations, and we use the clamped boundary condition, which replicates the real life scenario of the mills. Using certain dimensions and properties, we get certain frequencies, as you can see, for different mode shapes. Using the similar boundary conditions and dimensions, we then thus proceed with the model analysis and answers, and compare the simulation data with the theoretical data. And as seen, there are certain outliers with 7 to 8% degree, but most of the data is consistent with the theoretical data, and the simulation data is consistent. So thus we verified the accuracy of our simulation model. Then we proceeded to the analysis on the mill prototype itself with these dimensions, and having 6 liners inside the mill prototype. So as we saw earlier, there were numerous frequencies that we obtained for different mode numbers. for the consistency in comparison, we considered the bending mode frequencies. The first case we simulated was where we systematically removed liners one by one to see how the frequency varies. In the results, we saw that as we remove liners one by one, there's a certain percentage drop in the frequencies. The second case that we simulated was where we adjusted the line of one liner, keeping all the other liners intact. And we saw that the frequency also drops as the height of the liner reduces. Next is structural decoupling. In the first two cases I discussed, we just considered the mill by itself and there was no load present inside the mill. But that does not replicate the real life working conditions of the mill, because when the mill is in operation, there is a load present inside the mill and it has an effect on the frequency of the mill itself. So it becomes important to differentiate the frequency change due to the liner wear from load effects in the mill. While simulating the load present in the mill is a complex task and was out of the scope of our project. So to simplify that load, we replicated the load as a uniform layer of constant thickness so that it exerts similar forces that the load itself will exert on the mill surface. And when we increase the thickness of the mill surface, we found out that the frequency also increases. But these are all numbers. What does actually mean in real life? So talking about the first case, where the frequency dropped due to the liner removal. The key finding was that when we remove a single liner, there is a 17% decrease in the natural frequency of the mill. This basically gives us a threshold frequency to compare when we are monitoring the data, because this case replicates when a liner is completely broken and it reduces to zero height, so that we get a threshold frequency and build maintenance strategies based on the threshold frequency. The second case that we discussed was the frequency reduction in liner height. And we saw that there was a consistent frequency drop with decreasing liner height. These two, both the cases go hand in hand, and as we can monitor the frequency drop in the second case and build a time frame to predict when the frequency might reach the threshold frequency that we got from the first case. In the third case, I talked about the structural decoupling, where we figured that when there is a load present in the mill itself, the frequency is increasing. This helps us enables us accurate differentiation between the liner wear induced frequency variations and those caused by operational loads, and thus enhances precision in monitoring and maintenance. So to conclude that, to our project, we theoretically varied the model and with the simulation. And from the simulation results, we demonstrated that how the liner removal and wear impacts the frequency, and how it can help us to identify the critical thresholds for maintenance and fault detection. And through this, we can have an official benchmark that can help us to build a non-intrusive method to predict the liner degradation. I would like to acknowledge my university supervisors and the end-user partners as well as all the industry partners and supporters of the PRIF Consortium. Thank you.
Questions for Abhishek? Question? Well, I can start with a question. How do you think your approach can be applied or scaled to mills of different size? So how do you scale the approach to mills of different size?
So basically, the idea behind that is we can use a number of sensors. So the next step will be how to space the sensors and place it on the surface of the mills. So if there are larger scale mills, we can place a number of sensors so that it covers the whole area, and we can get an idea of the frequency variations throughout the areas. So as the size increases, we can increase the number of sensors that we place on the surface of the mill.
But the frequencies will be different too, so you're just going to scale then. So it's the same approach, but we will get different readings, different frequencies?
No, the frequencies will depend on the liner degradation itself. So that will be combined with let's say an encoder, we can place an encoder itself. So when we combine both the data of the sensors and the encoders, we can pinpoint the location where the frequency fluctuation actually occurs. And because the mill is in operation, there will be a frequency fluctuation, but we do have a threshold frequency for which we can focus on which area of the mill is actually giving us that fluctuation.
Okay, thanks. Any other question? You want to go, Nigel?
Are there any other things that you might want to try to further validate your results? And I'm thinking also about further research that might be continued to carry this work on. It's intriguing, and I can see that there's a lot of opportunities here to go on with it. So what are your thoughts on that?
Yeah, the further implication can be that we can actually get the data from the actual mill surface, and because this is basically this is simulation data, and how the real life data varies because the real life mills structurally are very different from what we did in the simulation. So we can compare the data to get an actual result. And we can also, as I said, work on the spacing of the accelerometers and the encoders on the real life mill, and how we can space them to get accurate data throughout the mill. So that can be a further research thing.
Excellent, thank you. And thanks also to your colleagues, because this was a group project. And for a master's student, you've done a fantastic job, and well done. Great presentation too.
Thank you.
Thank you.
Thank you.
Thanks, Abhishek.
Okay, so we are now having afternoon tea. We are now having a break for afternoon tea and have a chance also to have a chat between yourselves and have a look at the posters and interesting presentation at the back of the room. And what time we resume?
I guess about 20 past?
Quarter past?
20 past.
Okay, we aim for 20 past. Okay.